Welcome to the fifth online lecture. Um, Today and next week, we're going to look at what is known as probability theory, and that is part of inductive reasoning. So remember, we made earlier in the course a distinction between induction and deduction. Well, probabilistic reasoning is a form of inductive reasoning, and I usually teach this when I teach a critical thinking course. It seems to me that it's an important component of of critical thinking. So it's good. It's good to know probability theory, and this may actually help you in your lives. It's not just a dry academic subject. Okay, so let's start out then by so again this week. We'll talk about probability theory, and then we'll talk about it in more detail next week. Okay. So anyway, to start off, we need to define the concept of probability, right? We all use the term, but not everybody, but a lot of people don't have a precise definition of it. So, as I say here, for simple events, the probability of an event's occurring is the number of favorable occurrences divided by the number of total possible outcomes, right? So the chance of getting ahead when I toss a coin is 1/2. One is the favorable outcome, and two is the total number of possible outcomes, either head or tails, right? So as I have on the PowerPoint, then the probability of an event E equals X over N, where X is the number of favorable events or outcomes, and N is the total number of possible outcomes. All right. Now, basically, um, probabilities will be less than one because usually X is not equal to N, right? Um, but if a probability of an event is one, then that means the event must occur. Probabilities range from 0 to 1. All right. So, for example, there's no such thing as a negative probability. That doesn't even make any sense, right? I can't say the chances of winning Lotterio are -10, right? I mean, it's hyperbole, right? That's not true. The lowest odds would be 0. So probabilities always range from 0 to 1. So here are some examples of probability. There is the probability of getting tails on one toss of the coin. It's 1/2. The probability of getting 2 when I roll a die once will, of course, be 1/6, right? 2 is the favorable outcome, and 6 are the number of total possible outcomes. So one event is divided by 6, so 1/6. The probability of getting a king from a deck of cards. Well, if you know anything about cards, there are 52 cards in the deck. There are four suits. What is it? Diamonds, hearts, clubs, and spades. And so those are the four suits of the cards. And then within each suit, there are 13 cards, 1 through 10, ace up to 10, and then three what are called face cards, jack, queen, king. So um, in each suit, then there is one king, and altogether, then in a whole deck of cards, there are four, right? So therefore, the probability of getting a king from a deck of cards is 4/52. So let's look at the meaning of terms relating to probability. If the probability of an event is 0, right, then that means that the number of favorable outcomes is 0, right? So the probability that my laptop, while I'm giving this lecture, will turn over on its side by itself is 0, right? So no favorable outcomes over whatever n the number of outcomes is. So example, the odds of getting a joker from a deck of cards containing no jokers is of course 0, right? Divided by 52. The probability of an event is a positive number, greater than 0 but less than 1, means that the number of favorable outcomes is non-zero, but less than the number of possible total outcomes. So let's say that the chances of seeing a gray squirrel in my backyard is something like, let's say, 2 out of 100 or something like that, or 1 out of 50. All right. That means that the probability of my seeing a gray squirrel in my backyard will be 1/50. Okay. Here's another example. The odds of getting a king from a deck of cards is again 4 out of 52, right? Okay. On the other hand, the probability of an event is 1 means the event's occurring is certain. So that means that the number of favorable outcomes is the same as the number of possible outcomes, all right? So, for example, the probability of drawing a red ball from an urn containing only red balls is, of course, 1, right? Okay. Um, any ball you pull out of it will be red, so it's 1. It's a perfect probability. So therefore, to summarize, probabilities range from 0 to 1. A probability of 0 means the event is impossible, it cannot happen. A probability of event 1 means that the event is certain, it must happen. And in between 0 and 1, that means the event is likely to a certain degree, right? So that's the intuitive meaning of probability. I know a lot of people use the word a lot, the probability of my winning Lotterio, the probability of, let's say, it's raining tomorrow. We use the term all the time, but we generally don't know what it means. So one of my goals here is to give you a fairly precise definition of probability. The definition that we're working with is called the frequency definition of probability. Okay, so what we're going to look at now is, so what we've looked at so far are what you would call simple events, right? Like the chance of getting a king by making one draw on a deck of cards, the chances of getting a heads when I toss a coin, the chances of getting a 2 rolling a die, right? All of these are simple events, but you can also have events that are more complex. There are two main kinds of complex events. They're what are called conjunctive events and disjunctive events. Okay, so a conjunctive event will be, as it implies, a conjunction of two simple events. So, for example, A and B, getting snake eyes, rolling 2 dice simultaneously. So if I roll 2 dice and I get 1 and 1, that is a complex event. All right, the chance of getting at least 1 is a complex event. Um, okay, um, so that's a complex event. So and it's conjunctive because I get 1 on both on both die, right? So it's a complex conjunctive event, A and B. On the other hand, an event is disjunctive, A or B, just in case one or the other occur, or in some cases, possibly both. So the chances of getting either a king or a queen from one draw on a deck of cards, right, is a complex event. It's obviously, as you know, 8 out of 52, right? 4 out of 50, or 4 out of 52 plus 4 out of 52. So therefore, two kinds of complex events: conjunctive events, A and B, and disjunctive events, A or B. So what we're going to look at first in today's lecture is how to calculate the probability of a complex conjunctive event of the form A and B. And it actually, I mean, this, believe me, the math in elementary, now this is just elementary probability theory, but in elementary probability theory, the math is very simple, right? I know some people use combinations and permutations and so on, and you can use that if you want, or factorial notation. But what I'm giving you are very simple, sort of intuitive rules. So on the assignment, I would like you to use the simple rules that we're going over in the lecture today. All right. So anyway, as I say here then, to calculate the probability of a conjunctive event A and B, you simply multiply their individual probabilities. So the general formula for conjunctive probabilities is the probability of A and B equals the probability of A times the probability of B. All right. So what are the odds of getting snake eyes rolling 2 dice simultaneously? Well, it'll be the probability of getting a 1 on the one dice times the probability of getting a 1 on the other dice. So that is 1 over 6 times 1 over 6 equals 1 over 36. So my odds, if I'm rolling 2 dice, right, my odds of getting a snake eye is 1 out of 36. Here's another example. What are the odds of getting 2 heads in a row, tossing a coin twice? So let's say I take, I don't know, a quarter or a loonie or something like that, and I toss it twice. What are the odds that I will get 2 heads in a row, right? Well, again, The chance of getting ahead on the first toss is 1 out of 2. The chance of getting ahead on the second toss is 1 out over 2. So what you do then is you multiply those probabilities. So the chance of getting 2 heads is the probability of getting ahead on the first toss times the probability of getting ahead on the second toss, which is 1/2 times 1/2 equals 1 over 4, right? So as you can see, the math is very simple. It's just simple multiplication. Okay, what are the odds of getting 2 kings in a row drawing twice from a deck of cards? All right. Well, as I say on the slide, the answer depends. It depends on whether or not you replace the card in a deck of cards. Okay. If I draw a card and then I replace it, then the probabilities of the second event the probability of the second event is independent of the probability of the first event. But if I don't replace the card, then that will affect the probability of the second event. So let's say that I draw from a deck of cards and I replace the card that I drew. Then the probability of getting 2 kings in a row in that case is simply 4 over 52 times 4 over 52, right? 4 out of 52 for getting a king the first time, and then assuming I replace it and reshuffle the deck, the chance of getting a king the second time are still 4 out of 52. So using the multiplication rule for the conjunctive event of getting 2 kings will be 4 out of 52 times 4 out of 52 equals 16 over 2,704. So again, it's just simple mathematics, right? Simple, arithmetic, multiplication. Now, things get a little more complicated if the events are not independent. So suppose, for example, that I don't replace the king when I draw from a deck of cards. I think you would agree that that will affect the probability of getting a king the second time around for 2 reasons. One, there is 1 less king in the deck that I didn't replace. And 2, there is 1 less card in the deck, right? Given that I pulled a card. All right. So as I say here intuitively, we would expect that the chance of getting 2 kings in a row will be less if the first king drawn isn't replaced, right? The next time there will only be 3 kings left, so that's a lower probability. There were fewer kings in the deck for the second draw. So to accommodate these kinds of cases, we need to amend our probability rule, right, for when the events are not independent. For 2 events A and B, we say that A and B are independent if the occurrence of A has no effect on the probability of B's occurring. So let's say, for example, I play Lotterio, right? So I play Lotterio every week. And a lot of people say, well, look, if I keep playing it every week for 30 years, the odds are I've got to win. The odds are going to be in my favor. What they don't realize is that each draw from the lottery is independent of subsequent draws, right? Therefore, the fact that I've drawn on the lottery for 30 years is not going to affect the probability of winning the lottery the next time around because those events are independent. They don't affect one another. Same thing with 2 dice. Assuming that the dice don't collide, if I roll 2 dice simultaneously, assuming again they don't collide, then I think you would agree that the probability of getting a 2 on the one dice is completely independent of the probability of getting a 2 on the second dice. All right. So here are some examples then of independent events. Getting snake eyes on rolling 2 dice, assuming they don't collide, those are independent events. Getting 2 kings in a row, drawing from a deck of cards with replacement. Okay, those 2 events are independent. An event B, on the other hand, is dependent on an event A if the probability of B's occurring is influenced by the probability of A's occurring, right? So here are some examples of events that are dependent, that are not independent. Getting 2 kings in a row, drawing twice from a deck of cards without replacement, okay? So again, think about it again. Getting 2 kings in a row, drawing from a deck of cards without replacement. I think you'd agree that the first draw affects the probability of the second draw, right? That's just intuitive. In order to accommodate then the dependence of one event on another, we have to alter our rule for calculating probability a little bit, right? Okay. So in the case of the 2 kings, the probability of getting 2 kings in a row will be 4 out of 52, like the first time. But because there's 1 less king in the deck and 1 less card in the deck, the chance of getting a king the second time will now be 3 over 51, right? or 12 over 2,652, right, is the probability of getting two kings in a row if the king is not replaced. When there is replacement, the probability of getting two kings in a row is a bit higher, right? It's 4 over 52 times 4 out of 52. So as expected, then the probability of getting two kings in a row from two consecutive draws without replacement, it will be lower than the probability of getting two kings in a row when there is replacement. The modified rule for calculating the probability of conjunctive events is as follows. It's called the general multiplication rule. The probability of A and B equals the probability of A, just like before, we multiply times, but this case, it's not just the probability of B, it's a probability of B given A, because the probability of B is affected by A's occurring because those events are not independent, right? So the second multiplicand, or whatever the heck you call it, is the probability of B given A, right? Given A's occurrence. So when you have a little slash like that, B slash A, that means that we're looking at what is called a conditional probability. The probability of B on the condition that A occurred, right? So P, B given A means the probability of B's occurring on the condition that 8 has occurred, okay? So PBA then signifies what is known as a conditional probability, all right? Bayes' theorem, it deals with conditional probabilities, but I don't think we'll have time to get into it next week. We'll see, right? We'll play it by ear. All right. So in any case, there it is, right? Now, when A and B are independent, then the probability of B given A will simply be the probability of B, right? In other words, the conditional probability of B reduces to its absolute probability because the event B is not in any way dependent on event B. So when A and B are independent, the general rule applies, right? The probability of A and B is simply the probability of A times the probability of B. Does that make sense to everybody? Okay, so those are the rules for conjunctive events. And we're just right now, for simplicity, we're sticking to just two events, right? Next week, we'll look at more complex probabilities, like probabilities of, let's say, for example, a conjunction of three events, that sort of thing, right? But that again will be next week, all right? But this week, I want to keep it simple. I want us to get the simple concepts down pat this week, and then next week we'll add a few complications. And by the end of the second week, you should be pretty knowledgeable about elementary probability theory. Okay? All right. Now let's try a few problems just to make sure that we understand, right, the general principles. So as I say here, for the following problems, calculate the probabilities of the conjunctive events. And you need to determine whether you use the restricted or the general multiplication rule, okay? So let's do, a lot of times, if you've ever done a little work in probability theory, you know it's very popular to use either tossing a coin, rolling a pair of dice, or drawing from an urn, right? So suppose then there is an urn containing 10 balls altogether, and they are of different colors. 3 of the balls in the urn are red, 2 of them are uh, green, and 5 of them are blue. So it's 10 balls altogether, 3 red, 2 green, 5 blue. Now suppose I draw from that urn, okay? Then what are the odds of getting 2 red balls in a row with replacement? Well, here's the thing. Because I've replaced the ball, and of course, I'm assuming that you then re-randomize the urn, right? So assuming I've replaced the ball and I re-randomize the urn, then it would be fair to say that those two events are independent. The drawing the first time from the urn is completely independent of drawing the second time. Therefore, what I'm going to do is use the restricted rule, probability of A times probability of B, right? So it's going to be the probability of 3 over 10, right? That's the chance of getting a red ball from the urn. There are 3 reds, so 3 over 10 times 3 over 10, which will be 9 out of 100. So I think I have this. Yeah, so looking on the next slide then. So what are the odds of getting two red balls in a row with replacement? It's the probability of getting two red will be 3 out of 10 times 3 out of 10 equals 9 out of 100. And that's because the two events are completely independent of one another because I put the ball back in the urn and I re-randomize it, okay? Now, what about if I don't replace the ball? Well, I think you'd agree that that is going to affect the chances of getting a red ball the second time. All right. In fact, there will be one less red ball and one less ball in the urn. So therefore, the probability of getting two red balls if I don't replace will be 3 out of 10, right? That's the first time I draw. There are 10 balls in the urn. There are 3 reds, so 3 out of 10. The second time I draw, however, there are only 9 balls left and only 2 red left. So now my chance is 2 out of 9. So overall, then, the chance of getting 2 reds in a row will be 6 out of 90, right? 3 out of 10 times 2 out of 9. Okay, does that make sense, everybody? All right, let's try another one. What are the odds of getting red on the first draw and green on the second draw with replacement? Okay, so again, this time I'm replacing. And what's happening is that on the first draw, I get a red, right? And on the second draw, I get a green. So what are the chances of that happening? So as you see here below, then the probability of getting red on draw 1 on green and draw 2 is, you're going to again multiply, of course, right? And remember that you've replaced, so the events will be completely independent of one another. All right. So it will be 3 out of 10 the first time I draw. That's my chance of getting a red the first time are 3 out of 10. And my chances of getting a green when I draw the second time are 2 out of 10. So I simply multiply those, right? The probability of red 1 and green 1 is simply the probability of red 1 times the probability of green 2 equals 3 out of 10 times 2 out of 10 equals 6 out of 100. So the chances then of getting a red ball, a green on the first, or sorry, a red on the first and a green on the second will be 6 out of 100 or 0.06. Okay, is that intuitive to everybody? All right, next one. What are the odds of getting red on the first draw and green on the second without replacement? All right, so let's think about this a second. So it's the same thing. I get a red on the first and a green on the second, but this time I didn't replace the ball that I withdrew from the urn. Well, that's going to affect the odds of getting a green ball on the second time, even though green ball wasn't chosen, because there's one less ball in the urn, right? So my revised rule then is that the probability of getting a red on the first and a green on the second is 3 out of 10 times 2 over 9. 3 out of 10 the first time, right? There are 3 red balls, 10 balls in the urn. The second time, there are only 9 balls now because I took out a red one and didn't replace it. But there's still 2 green, so the chances are then 2 out of 9 on my second draw of getting a green. So therefore, you'd simply multiply them together. 3 over 10 times 2 out of 9 equals 6 out of 90, right? Those are the odds of getting a red first and a green second if I did not replace the ball I draw the first time. Then that means that there is some dependence of the second event on the first. Okay, so is everybody good on that? All right. So just to review then, for conjunctive events, probably of conjunctive events, the rules are very straightforward and simple. It's the probability of an event A. So again, when if the events are independent, the probability is the probability of A times the probability of B. So the chance of getting 2 kings in a row from a deck of cards with replacement is simply 4 out of 52 times 4 out of 52. But if I don't replace, then we have a revised rule, right? And the revised rule is that the probability of A and B will be the probability of A times the probability of B given A, because the second event is dependent on the first, right? Okay, so that then is our amended rule that the probability of A and B equals the probability of A times the probability of B given A if the events are not independent. All right, so that's how you calculate the probabilities of conjunctive events. And as you can see, the calculations are not that difficult. And then we just did some examples together, right? Okay, all right. Now we're going to look at the calculating the probability of a disjunctive event. So remember, a disjunctive event is a probability of A or B. For example, the probability of getting at least one head on 2 tosses of a coin, okay, that will be a disjunctive event. The probability of getting a head on the first toss or the probability of getting a head on the second toss, right? Okay, so the probability of getting a head or a head, right? So suppose I draw then from a deck of cards and I want to know the probability of my getting either a king or a queen, okay? The probability of getting either a king or a queen. Well, it's going to be a disjunctive event, right? It will simply be all that you do. Now, with conjunctive events, you multiply. With disjunctive events, you add. So the probability then of my getting a king or a queen will simply be the probability of getting the probability of getting of getting a king or a queen will be the chance of getting a king, which is 4 out of 52, plus the chance of getting a queen, which are 4 out of 52, right? So with disjunctive uh, events, you add. You don't multiply, you add. So don't confuse that, right? For conjunctive events, you multiply. For disjunctive events, you add. So the chances then of getting a king or a queen will be 4 out of 52 plus 4 out of 52 equals 8 out of 52. Okay? Let's try another one. The chances of getting either a 1 or a 2, rolling a die once. All right? So I roll a die once. What are my chances of getting either a 1 or a 2? Well, the chance of getting a 1, as you know, is 1 out of 6. The chance of getting a 2, as you know, is 1 out of 6. So we add the events together, right? 1 over 6 plus 1 over 6 equals 2 over 6, or 1 out of 3. So my chance of getting a 1 or a 2 on rolling a die once will be 1 out of 3. So more generally then, the rule for disjunctive events is as follows. The probability of A or B equals the probability of A plus the probability of B. Okay, so that's easy enough, right? Remember, as I said at the beginning of the lecture, these rules are really easy, right? It's just multiplication and addition. That's honestly all it is, right? Okay, but of course there are complications. There are always complications, right? So here it is. What are the odds of getting at least one head on 2 tosses of a coin? All right. Now, this is a little bit tricky. You can't just add the events. All right. If you just add the events together, you will see that you get 1. So something is wrong there. Okay. The chance of getting at least one head when I toss a coin twice is not 1, is it? Right. It's much less than 1. So what the heck went wrong then? So let's consider then all of the possible outcomes. There are altogether, when you toss a coin twice, there are four possible outcomes, right? You could get heads, heads. You could get heads, tail. You could get tail, head, or tail, tail. So head, head, head on the first toss, tail on the second toss, or you could get a tail on the first toss and a head on the second toss, or you could get 2 tails. So if you look at all the possible outcomes and you count them out from that little matrix I put on there, you can see that altogether the chances of getting at least one head are 1, 2, 3, right? HH, HT, and TH. All right. So so that's elementary enough, right? So that's the probability then of getting at least one hit. It's not 1, because tail tail doesn't count as an event where you get at least one head. So there are only 3 events that count: head head, head tail, tail head. We can see then that 3 of the 4 possible outcomes involve getting at least one head. So the correct answer is not 1, but 3 out of 4, right? Okay, so what went wrong with our initial calculation is that we effectively counted head head twice, and that's why we ended up with one. So in other words, head 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 tail, right? 1 2 head head tail head 1 2 2 plus 2 equals 4 out of 4 equals 1, but you shouldn't count head heads twice. You only count it once. So there is a mathematical correction so that you don't count an event more than once when you're enumerating what are the successful outcomes. Okay. So as I say here, to compensate for counting the event head head twice, we can modify our rule for addition by subtracting from the disjunction the probability of getting heads on both, right? So what we didn't do is, so in other words, when we're subtracting that, what we're assuring is that we're not going to count the event head head twice. So the probability then of getting at least one head is the probability of getting a head on the first toss plus the probability of getting a head on the second toss minus the probability of getting both heads, right? And we get then what we would expect: 1 minus 1/4 equals 3 out of 4, right? So again, how did I get 1/4? Well, the probability of getting ahead on the first is 1 over 2. The probability of getting ahead on the second is 1 over 2. 1 over 2 times 1 out of 2 equals 1 over 4. Therefore, um, although pH1 and pH2 add up to 1, that is 1 out of 2 plus 1 out of 2, I subtract from that 1 over 4 for the possibility of getting heads on both, right? And so we get the correct answer, which is 3 out of 4. So that's an important caveat, an important modification to the rules for calculating disjunctive probabilities. So again, notice that when I toss a coin twice, one possible outcome is that I get 2 heads, right? So getting a head on toss 1 and a head on toss 2 are not mutually exclusive events, right? Two events A and B are mutually exclusive if they can't both occur. I just wanted to make sure there was an extra slide that I just wanted to make sure was there. Sorry about that. My apologies. Okay. So anyway, so as I say here then, so when I toss a coin twice, one possible outcome is I get 2 heads. Getting a head on toss 1 and a head on toss 2. And they are not mutually exclusive events, right? So two events, A and B, are mutually exclusive. They can't both occur. So if I say, what are the chances of getting 2 heads on a toss of the coin? Getting a head on toss 1 and getting a head in toss 2 are not mutually exclusive. They can both occur, right? Okay. So again, that's why I need to then subtract the probability of getting both from the overall probability to get the correct answer. It's so that I don't overcompensate, right? So again, so what is mutually exclusive? Two events A and B are mutually exclusive if they cannot both occur at the same time, right? So when two events A and B are not mutually exclusive, then they can both occur, and we need to subtract the probability of both A and B. But if they're not mutual, but if they are mutually exclusive, then you don't need to subtract anything because they can't both occur. So the probability of them both occurring will be 0, right? So therefore, the rule for calculating the probability of disjunctive events when they are not mutually exclusive is, as I have written at the bottom there, the probability of A and B equals the probability of A plus the probability of B minus the probability of A and B. And that is called the general addition rule. So when two events A and B are mutually exclusive, then we simply use our original rule. This is called the restricted addition rule. Okay. When A and B are mutually exclusive, then the probability of A and B will be 0. And so the general addition rule then reduces to the restricted rule. One other example: what are the odds of getting at least 1 rolling 1 1 rolling on rolling 2 dice, right? Okay. Well, if you just use the simple addition rule, you're going to get the wrong result, right? If you use the simple addition rule, you're going to have 1 over 6 plus 1 over 6, right? And if you add those together, you get 1 over 3. But that probability is actually too high because you can also get 2 ones in a row, right? So the probability of getting at least 1 must also include the chance of getting 2 ones. So you need to subtract that from the overall probability. So what are the chances then of okay. So in any case, so right now then we have 2 over 36. However, the chances, or 1 over 3 rather, sorry. So the chances then of getting um, at least 1 when you subtract the chance of getting both, then it's going to be this, right? The chance of getting both would be 1 over 6 times 1 over 6, which would be 1 over 36. So then you have to subtract 1 over 3 from 1 over 3, 1 over 36, okay? And that will give you the correct answer, right? Sorry, this is missing a slide. I'll add that to the one that I have posted on the lecture. So my apologies for that. But in any case, so that's what you do. So it's not going to be just 1 over 3. Yes, you do add 1 over 6 plus 1 over 6, but but you subtract from that 1 over 6 times 1 over 6, which is 1 out of 36. So the correct probability for getting at least 1 is 1 over 6 plus 1 over 6 minus 1 over 36. Okay, and that will give you the correct probability. So for example, that would be, let's just do a little bit of math here. So 1 over 6 is what? What is that out of 36? That's 6 out of 36 plus 6 out of 36, right? And then you subtract from that 1 out of 36, so that would be 11 out of 36. So the chances of getting then at least 1 is not 1 out of 3, because you have to subtract from that event the probability of getting a 1 on both die, right? And so then that means, so doing the math then, it's 6 out of 36 plus 6 out of 36, which is what, 12 out of 36 or 1, 3, minus 1 out of 36. That's the probability of getting ones on both die, right? And so what you'll end up with is not 12 out of 36, but rather, or 1 over 3, but rather 11 out of 36. Okay, does that make sense? So be careful with that, right? You have to, when you're calculating disjunctive events, you always have to take into account the probability of they're both occurring, and you have to subtract that. Okay, so just to review for a second. So what we did is we looked at how to calculate the probability of disjunctive events. When the two events are mutually exclusive, then the probability of the disjunctive event is simply the probability of the first plus the probability of the second. That's called the simple or restricted conjunction rule. So more generally, as I have in the bottom of the slide, the probability of A or B is simply the probability of A plus the probability of B. The chances of getting either a 1 or a 2 on rolling a die, that's just on one die, right? Not two. So don't conflate this with what we just did, is going to be 1 over 6, right? Because the chance of getting a 1 is 1 over 6. I add to that the chance of getting a 2, which is 1 over 6. So you add those together and you get 2 over 6 or 1 out of 3. 1 out of 3 are the chance of getting either a 1 or a 2 on rolling a die just once. Okay? So that is for when the events are mutually exclusive. They can't both occur. But things get a little messy when you have events that are not mutually exclusive. When two events are not mutually exclusive, then you need to subtract from your overall probability for their disjunctive occurrence. You must subtract from that the probability of their joint occurrence, right? So again, looking at the coin in the heads example, the chance of getting at least one head, it's 1 over 2 plus 1 over 2. But because you could get heads on both tosses of the coin, you have to subtract from that the probability of getting 2 heads in a row. So it'll be 1 over 2 plus 1 over 2, right? Minus 1 over 2 times 1 over 2, or 1 over 4. All right. And that, in fact, will give you 3 out of 4. So it's not 1, it's 3 out of 4. And so in general, then, this is at the bottom of this slide, the rule for calculating disjunctive probabilities, the probability of A or B, will be the probability of A plus the probability of B. But in this case, you subtract the probability of the joint occurrence, right? So the chances of getting ahead the first time and the chance of getting ahead a second time is 1 over 2 plus 1 over 2. The probability of getting 2 heads in a row, remember that now 2 heads in a row is a conjunctive event, so we multiply those, minus 1 over 2 times 1 over 2, minus 1 over 4. So this is called, as I say here, the general addition rule. And then we looked at the slightly more complex example where, let's say, I roll 2 die and I want to know the problem, or sorry, not the problem, the probability of getting, let's say, of getting at least 1. All right. Well, very simple. 1 over 6, right, for the first dice. Add to that 1 over 6 for the second dice. Again, that's, remember, with disjunctive events, you add. With conjunctive events, you multiply. But I have to subtract from that the chances that I could get a 1 on both tosses, right, or on both die. So then it would be 1 over 6 plus 1 over 6, or 6 out of 36 plus 6 out of 36, which is 12 out of 36, minus the chance of getting 2 1s in a row, right? Well, that will be 1 over 6 times 1 over 6, which is 1 over 36. So it's 12 out of 36 minus, right, 1 over 36, which will be actually 11 out of 36. So you always have to subtract, the event, the joint event, right? But that again is only in the case when the two events are not mutually exclusive, when they can both occur. Okay, so let's try this then. So as I say here, let's get a little more practice. So let's say I have an urn, and I have altogether again 10 balls in the urn. Let's say 2 red, 2 green, and 6 blue. Okay. So now what I'm going to do is I'm going to use the disjunction rule to calculate these probabilities, the probabilities of disjunctive events. So first of all then, what are the odds of getting at least 1 red with replacement? So I should mention, I guess I should mention that you're drawing twice, right? So my apologies for that. So you're drawing twice from the urn. And let's say that each time the first time you draw, you replace the ball you drew, re-randomize, and you draw a second time. So I think you'd agree that those two events are, first of all, independent of one another. But at the same time, it is possible that I could get 2 reds in a row. So you have to subtract them, the chance of getting 2 reds in a row, from getting the chance of getting a red in the first and then getting a red in the second. So overall then, the probability of getting at least 1 red is 2 over 10, right? So 2 over 10 is the chance of getting at least of getting a red the first time I draw, plus 2 over 10. 2 over 10 is the chance of getting a red the second time I draw. Then you subtract from that the chances of getting 2 reds in a row. Well, the chance of getting 2 reds in a row will be 2 over 10 times 2 over 10 equals 4 over 10. Or sorry, 4 over 100. Or yeah, 4 over 100. So basically then, overall, when I do the math, it's 2 over 10 plus 2 over 10 equals 4 over 10 minus 4 out of 100. 4 out of 100 are the chances of my getting, are my chances of getting 2 reds in a row. So the overall probability then is 36 out of 100, or 0.36. 0.36 are the odds that I'll get at least 1 red drawing twice from the urn with replacement. But it can get a little more complicated. Suppose that I don't replace after I draw the first time, okay? So what are the odds of getting at least one red without replacement? Well, it's a little more complicated this time because although I could still get two reds in a row, the chance of getting a red the second time are going to be different because of my drawing red the first time, right? Because now there's no replacement. So those two events are no longer independent of one another, right? So let's look here. Let's look at my calculations. The probability of getting at least one red when I do not replace will, as before, be 2 over 10 plus 2 over 10. That doesn't change. But now the joint event that I'm subtracting is different because the second time I draw, there's one less red ball in the urn and one less ball in the urn. So therefore, the chance of getting two reds in a row will be 2 out of 10 times 1 over 9. Remember that we're using now conditional probabilities, right? 2 over 10 times 1 over 9. And if I did the math correctly, it should be 34 over 90. Does that make sense to everybody? Okay, so notice then the difference between the first calculation and the second. In the second calculation, I'm still subtracting the probability of the joint occurrence of getting reds on both draws. But the second time around, because I don't replace, then what I have to do is to take into account that I didn't do that. And so the second time I draw, there'll be one less red ball in the urn and one less ball in the urn. So it'll be minus 2 over 10 times 1 over 9 equals 34 over 90. Okay. So far, so good? Okay, next one. What are the odds of getting a red on the first draw or a blue on the second draw with replacement? So think about it again. This is not a conjunctive event. I'm not saying what are the odds of getting a red in the first plus getting a blue on the second, right? Which then I would use the multiplication rule. This is not a conjunctive event. This is a disjunctive event. What are the chances that when I draw from the urn, either I get a red ball on the first draw or I get a blue ball on the second? I think you would agree that those are different kinds of events, right? So what do I do? How do I calculate the chance of the disjunctive event? So the probability then of getting a red on the first draw or a blue on the second draw is 2 out of 10 because it's two red balls, right? 10 balls plus 5 out of 10, five blue balls, right? And 10 balls. So it's 2 out of 10 plus 5 out of 10. But I have to subtract from that the joint occurrence because it is entirely possible, right? It is entirely possible that I could end up the next time around. It's entirely possible the next time around that I get a blue. So in other words, I get a red in the first and a blue in the second. Both of those could happen. So I have to subtract then that joint probability from the addition, right? So it's 2 over 10 plus 5 over 10 minus. So what you see in the parentheses there, that's the probability of getting a red on the first draw and a blue on the second draw. Well, that is, of course, 2 over 10 times 5 over 10. And if I did the math correctly, that's what, 1 out of 100? So it's 7 over 10 minus 1 over 10, because 10 out of 100 is simply 1 over 10. So the chances then of getting a red on the first or a blue on the second with replacement is 6 over 10, right? 6 out of 10, or 0.6. Okay, now what about if I don't replace? Well, that will actually make a difference, right? If I don't replace, that will definitely make a difference. So let's say I make a draw the first time and I make a draw the second time, but but after I draw the first ball, I don't replace it. Okay, so I don't do anything. I don't replace the ball. So that's going to affect those two events. Then will be independent of, or rather will be dependent on one another. If I draw the first time, but I don't replace, that is going to affect the probability of the second events occurring, right? So when I multiply their conjoint probability, their multiply to get the conjoint probability of both events occurring, I have to take into account the fact that the second time I draw, the probability has been affected by the first draw that I made. In other words, those two events are not independent. So it's basically the same, except now what I'm subtracting will be a little bit different, right? To take into account the fact that the probabilities have changed by making a draw the first time. So therefore, the probability of getting a red on the first draw or a probability of getting a blue on the second draw is 2 over 10 plus 5 over 10, right? 2 over 10 because the two red balls in an urn of 10. The second atom, well, whatever you call it, the second quantity, addendum? No, it's not addendum, but anyway, the second quantity will be 5 out of 10, right? 5 blue balls, 10 balls. But now I'm going to subtract the chance of getting both. It's entirely possible that I could get not just a red or a blue, but I could end up getting a red and a blue. A red on the first draw and a blue on the second, okay? All right, that's fine. Well, then that's going to be 2 over 10, because there are 2 balls in the urn, times 5 over 9. Right? Because now there is less one ball in the urn, right? So does everybody see then why it's 5 out of 9 and not 5 out of 10, right? Because again, then this time there is one less ball in the urn. So I didn't have time to do the math. You can do, I'll leave that up to you. So it'll be 7 over 10 like before, minus, what is it, 10 over 90, whatever that is, right? And that will be your final result. Okay, so hopefully I've done enough examples with you that you will be able to do the next assignment. Okay, it shouldn't really be a problem. I'll also post some suggested exercises that you can work on in the lab with your GA. All right, and then on Thursday, I will post the next assignment, and on that assignment, I will ask you to do some of the problems we did in today's lecture. Okay, so today's lecture is a little bit on the short side. It's short and sweet. I didn't want to throw too much stuff at you, right? I didn't want to do the complementation rule because that's a whole other subject in and of itself, right? So we'll leave that till next week. Let's just do this stuff for now, and I would just want to make sure you understand this, and then we'll go to slightly more complicated things next week, right? So one thing at a time. We'll do it in phases. All right. So thank you very much for your time. And I will be sure to post those suggested exercises sometime this evening. Work on those with your GA lab. And then on Thursday, I'll post the assignment. Okay. All right. So have a great day, a great week, actually, because it's a whole week coming up. And I'll be back online next weekend to give you the lecture on what is known as the complementation rule. Take care. Thank you.